So let us now start this lecture with ideal gas equation. So before this, whatever laws that we studied about the various gas laws, that was the Boyle's law, Charles' law, Gay-Lussac's law, and the last one was the Avogadro's law. So all the laws that we studied was for ideal gas, right? So let us now study the ideal gas equation, which is the combined form of all the laws, all the four laws basically. Four laws, or we can say three laws, because we saw that Gay-Lussac's law can be derived from Boyle's law and Charles' law only. So let us start. The three laws which we have learned till now can be combined together in a single equation, and that is known as ideal gas equation. Okay, so we know that Boyle's law was at constant temperature, so volume was inversely proportional to pressure. Charles' law was at constant pressure, and where volume was directly proportional to temperature. Avogadro's law was at constant temperature and pressure, and V was directly proportional to N. So here you can see that in all the three laws, here in the left side we are having V, and in the right hand side there are different variables. So we can combine this and write it as V is directly proportional to N into T upon P. So N and T will be up because it is directly proportional, and P is inversely proportional. So it is here also it is inversely proportional. So, and just before, like we did, so in order to remove this proportionality sign, we need to introduce a proportionality constant R. So, and therefore equal to will be substituted here. So R is the proportionality constant. So on rearranging, you can have this equation of PV is equals to nRT. Or another arranged form is R is equals to PV upon NT. And R is also called the proportionality constant, or it is also called the gas constant. It is same for all the gases. Okay. Therefore, it is also called the universal gas constant. Equation 5.17 is the ideal gas equation. So this derivatization is very important. And also we need to learn this ideal gas equation. Equation 5.1, it shows that the value of R depends upon units in which P, V, and T are measured. If three variables in these equations are known, fourth can be calculated. Okay. So from this equation, we can see that at constant temperature and pressure, n moles of any gas will have the same volume because V equals to nRT upon P, right? So here we saw that R, which is a constant, so at for any pressure, volume, N, and temperature. So here in this equation, the which gas we are talking about is not new. It is actually valid for all the ideal gases. Okay, so for all the ideal gases, be it helium, be it neon, be it hydrogen gas, whatever the gas should be ideal at that time, pressure and volume. So whichever gas, so the R will be constant for all the gases, and that is why it was called universal gas constant, right? So if at any, any temperature, if we put any three variables, a particular value, okay. So if, for example, at a constant, that is what it is written over here. At constant temperature, pressure, n moles of any gas will have the same volume, right? So if you are keeping T and P constant, okay, then an R is already a constant. So at any temperature and pressure, any ideal gas, so any n mole of any ideal gas, X, Y, Z, any ideal gas, if you are taking n mole, then the volume exerted by all the gases will be same. Okay, so this equation will be applicable to any gas under those conditions when behavior of the gas approaches the ideal behavior. So volume of 1 mole of an ideal gas at STP, what we studied was 22.710981 liter per mole, right? So the value of R for 1 mole of an ideal gas that can be calculated under these conditions. So at STP means R equals to, we are talking about here, we are substituting all the standard temperature and pressure, okay? And N also for 1 mole we are talking about. So what will be the R value? So if we put every constants to these variables, then we can easily find out the value of R at STP. So here pressure should be 10 to the power of 5 Pascal. That is a standard pressure. Volume is 22.71 into 10 to the power of minus 3 meters square. It is also at constant and at STP. Now N is 1 mole and temperature is 0 degrees centigrade, or we can say 273.15 Kelvin. So if we put all of these values, and you will get the value of R as 8.314 in Joule per Kelvin per mole. Okay, so at STP condition used earlier, that is 0 degrees centigrade and 1 atm pressure, the value of R is 8.2 into 10 to the power of minus 10 liter atm per Kelvin per mole. So you will see that it is different for different values, right? Different units give different value of R. You need to put this value of R depending upon what type of unit is used in the question. If the pressure is given in atm, then you will use, and the volume is given in liter, then you will use this equation. If the temperature is given in if the energy, if it is given in the pressure is given in pascals and the volume is given in meter square, then you need to follow this value. Okay, so the ideal gas equation is a relationship between the core variables and it describes the state of any gas. Okay, for it is only valid for ideal gas, definitely. So it is also called equation of states. Okay, so it will tell you what is the state of any gas at any temperature, pressure, and volume. Okay, let us now go back to the ideal gas equation. So this is the relationship for the simultaneous variation of the variables. If temperature, volume, and pressure of a fixed amount of gas varies from T1, P1, and P1 to T2, P2, and P2, then we can write it as like this, right? This is one ideal gas equation at T1, V1, and T1, V1, and P1. This is another ideal gas equation at T2, V2, and P2. But NR will be same, right? So you can also equate this side and this side. So this is the equation 5.19 you will get. So equation 5.19 is very useful equation. So if out of 6 values, 5 variables are known, then you can easily find out the 6th one by solving this equation 5.19. So this equation is known as combined gas law. Now we will be solving problem number 5.3 based on this. So at 25 degrees centigrade and 760 mm of Hg pressure, a gas occupies 600 milliliter volume. What will be its pressure? So P2 is not given at a high to a temperature, that is T2 is 10 degrees centigrade and V2 is 640 millimeter. First of all, whatever pressure, volume, temperature, P1, T1, P1, P2, P2, T2, everything you need to write it down. And after you, so P1 is given as 760 mmHg, P1 is given as 600 milliliter, temperature is given as 25 degrees centigrade, which you need to convert it into Kelvin only all the time. So it is 298 Kelvin, and V2 is given 640 milliliter, and the T2 is again in Kelvin. Here you don't need to change any units because ultimately the units will cancel out each other. So, and only the unit of here what is asked? Pressure. So only the unit of pressure, that is mm of Hg will be left, and that will give your answer in also mm of Hg. So here you will put all the equation and you need to solve this equation and you will get the answer. So there was no toughness in this question. So let us now move forward to this 5.6.1 unit, which is density and molar mass of a gaseous substance. Okay, now we are correlating density and molar mass from this ideal gas equation. So we know that the ideal gas equation was PV equals to nRT, and then you will arrange it in such a way you can write it as N upon V equals to P upon RT. Now you need to introduce the term density. So how can you do that? So density is nothing but mass upon volume, and also moles is equals to mass upon molar mass. So you can write moles as mass upon molar mass. So when you write it as like this, then this M and this upon volume, you can write it as density, and density upon molar mass equals to PRT. And if you arrange it as, then you can easily find out the molar mass of any gas, ideal gas. when you know its density and temperature and pressure. Okay, so basically you can identify the gas from its density at given temperature and pressure, right? So Dalton's law of partial pressure. So let us study a very important topic which was given by Dalton, which is Dalton's law of partial pressures. So the law was formulated by John Dalton in 1801. It states that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressure of individual gases. So supposingly you have, for example, you have mixture of gases A, B, C, different types, three types of gases are there in the container, and you have all of these mixture. You know that the gases are always uniformly arranged. So it is always uniform mixture. So now the pressure, the total pressure is exerted by that gas. Okay, the total gas will be equal to the sum of the partial pressure of each gases. One note is there: the gases should not be reactive to each other. It should be inert. Okay, they should not react with each other. That is the pressure with which these gases would exert if they were enclosed separately in the same volume and under the same conditions of the temperature. In a mixture of gases, the pressure exerted by the individual gas is called the partial pressure. So P total will be equal to the partial pressure of 1, partial pressure of 2, partial pressure of 3, third gas, right? So where P total is the total pressure exerted by the mixture of gases, and P1, P2, and P3 are the partial pressures of gases. Now, gases are generally collected over water and therefore are moist. So, pressure of dry gas can be calculated by subtracting the vapor pressure of water from the total pressure of the moist gas, which contains water vapors. Now, pressure exerted by the saturated water vapor is called the aqueous tension. So, if you want to take out the pressure of the dry gas, then you can subtract the pressure of the water vapor by the total pressure. Okay. Now let us study the partial pressure in terms of mole fraction. So we know this is the ideal gas equation. So you can arrange it as P1 equals to in terms of pressure. So it will be like this. Now you need to convert it into mole fraction. So what exactly is mole fraction? It is the mole of that gas upon that particular gas 1 upon upon the sum of all the moles of the gas. So what you will do is that you have all these three pressures, okay, these three partial pressures, and you have written it in the form of moles, okay. Now, where N1, N2, and N3 are the number of moles of these gases. Thus, pressure for you just now have to put all of these three equations into this Dalton's Dalton's law of partial pressure, okay. And then, if you get this, then you can write it as like this. Now, you can, and it is that if RT upon V, what you can write it as P total will be equal to N total RT upon V, right? So you can change this RT upon V by PT upon NT. So that is what is done over here. So if you do it like this, then you can get the value, and we know that N1 upon NT is equals to mole fraction of 1. Similarly, N2 and N3 also. So you will, when you solve this, then you will get the equation as this one. So this is what? So now for each gas, so P1 upon P total is equals to N1 upon N1 plus N2 plus N3, right? So that means P1 upon P2 equals to Xi, that is the X1, mole fraction of 1. So P1 equals to the mole fraction of 1 into P total, right? So this is a very important equation that comes in picture. So the partial pressure of 1 will be equal to the multiplication of mole fraction of 1 into total pressure. Okay. Now let us solve the problem number 5.4. A neon dioxygen mixture contains 70.6 gram of dioxygen and 167.5 gram of neon. So there is a mixture of gas which contains two types of gases of dioxygen and neon, and the mass of these two are given, like the amount is given. If the pressure of the mixture of gases is in the cylinder is 25 bar, that means total pressure is given. What is the partial pressure of dioxygen and neon in the mixture? It's very simple. You need to find out the mole fraction first. How you will do that? You first need to find out the moles of dioxygen. You need to divide 70 upon 6 by the molar mass of dioxygen, and similarly you will do it for neon. So that will give you a number of moles for dioxygen and number of moles for neon. So the addition of the two moles will give you total number of moles, and that is why you can find out mole fraction of dioxygen by dividing the number of moles of dioxygen by total number of moles, and similarly you can find out the mole fraction of neon by dividing the by dividing the number of moles of neon upon total moles of the gases. Now you have the mole fraction of these two gases. Also, you have the total pressure. Now you can easily find out the partial pressure. So the partial pressure of oxygen will be equal to mole fraction of oxygen into total pressure, and partial pressure of neon will be equal to mole fraction of neon into total pressure. And that is what is given done over here. Now, let us study the kinetic molecular theory of gases. So far, we have learned the laws, that is the Boyle's law, Charles' law, etc., which are concise statements of experimental facts observed in the laboratory of scientists. Okay. Now, conducting careful experiment is an important aspect of scientific method, and it tells us how the particular system is behaving under different conditions. However, once the experimental facts are established, a scientist is curious to know why the system is behaving in that way. For example, gas laws help us to predict that pressure increases when we compresses the gas. But we would like to know what happened if at the molecular level when a gas is compressed. Okay, so we know that if you compress the gas, then the pressure will increase. But what is actually happening in the molecular level? That also is very important to know. So a theory is constructed to answer such question. A theory is a model, that is a mental picture that enables us to better understand our observation. Okay. So at higher pressure when you compress the gas, pressure is increasing. So this is one of the observation. But when you give a theory to this, then you can better understand this observation. So the theory that attempts to elucidate the behavior of gases is known as the kinetic molecular theory. So this molecular theory, the kinetic molecular theory, will tell you what actually happens at the molecular level, okay, of such laws. Assumptions or postulates of the kinetic molecular theory of gases are given below. So in order to give some theory, you need to postulate and assume something. So these are the various assumptions or postulates that is followed for the studying the kinetic molecular theory of gases. So these postulates are related to atoms and molecules which cannot be seen. Hence, it is said to provide a microscopic models of gases. Okay. Now, gases consist of large number of identical particles. It can be atoms or molecules. So that are so small and so far apart on the average that the actual volume of the molecule is negligible in comparison to the empty space between them. Okay, so they are considered as point masses. This assumption explains the great compressibility of gases. Okay, I think you are understood this point. So let me draw one thing. Suppose we have a container. So we are talking about gas in this container, okay? And we have gaseous molecules. It is written that the gaseous molecules are so small and so far apart that the volume of this whole container, that the volume of this actual gas molecules or atoms is negligible in comparison to the total volume of the gas. Okay, and that is why, and this explains that why the gases are so much compressible, right? I hope I'm clear. There is no force of attraction between the particles of a gas at ordinary temperature and pressure. The support for this assumption comes from the fact that gas expands and occupies all the space available to them. Yes? So this is the volume V. This is the volume V of the gas, right? So V is also the volume of the container. So at normal temperature and pressure, when you change the container now, and you change the container, and now the shape of the container is like this, okay? And then you and has the volume V2. So if you transfer all the gases to this container, so now the volume of gas will be V2 again. So that this means that there is no force of attraction between the gases, or we can say it in other words that the force of attraction between the molecules or atoms in the ideal gas at normal temperature and pressure is negligible because it tends to expand according to the container. Okay. Now, particles of a gas are always at constant and random motion. If the particles were at rest and occupied fixed position, then a gas would have fixed shape, which is not observed. This is very, very true. I think it is understood. Also, particles of a gas move in all the possible direction in straight lines. During their random motion, they collide with each other and with the walls of the container. So pressure is exerted by the walls as a result of collision of the particle with the walls of the container. So this thing I have already told you guys that how the gas exerts pressure in any container because of this colliding motion. So that this gas molecules collide with the walls of the container, and that is and this is this colliding thing is constant in all the direction because gas particles are always moving in all the possible direction. So the pressure exerted by the gas on the container is always same in all the direction. Okay, has to be same. Now, collisions of the gas molecule are perfectly elastic. So if it was not elastic, then what would have happened? Okay, so this means that total energy of the molecules before and after the collision is constant. Okay, so when the collisions are inelastic, then the motion or the energy of the atom or molecule before collision and after collision doesn't match. But if the molecules or atoms collides in an elastic fashion, in that case, the total energy of the molecule is conserved. Okay, so they may exchange the energy between the colliding molecules. Their individual energies may change, but the sum of the total energy in that container will always be constant. There will be no energy that will be dissipated. Okay, so if there were loss of kinetic energy, the motion of the molecule will stop and the gas will settle down after a particular time, but that doesn't happen, right? So this means that the total energy or the thermal energy is always constant of the gases. Okay, at a particular time, different particles in a gas have different speeds and hence different kinetic energies. Now, all the particles in the gas, you cannot think that all the particles in gas will have same speed. One can have more speed, one can have lesser speed, right? So different kinetic energies will be there for every particle. So this assumption is very simple because as the particles collide, they expect their speed to change. Yes, obviously this happens. Even if initial speed of all the particles was same, the molecular collision will disrupt this uniformity, and as a result of which there will be different kinetic energies for different atoms and molecules. Now, consequently, the particles must have different speeds which go on changing constantly. It is possible to show that though the individual speeds are changing, the distribution of speeds remains constant at a particular temperature. Okay, it is just similar to that of the previous point, but in that point we were talking about energy. Here we're talking about the speed, or we can say kinetic energy. Okay. Now, the last point, if the molecule has variable speed, then it must have a variable kinetic energy, right? So under this circumstance, we can talk only about the average kinetic energy. So you don't talk about the kinetic energy of the gas, and you always say average kinetic energy of the gas molecules because in that gas, all the molecules have different kinetic energy, so you cannot say kinetic energy because you have to say a broader term, which is average of all the kinetic energies of all the molecules. So in kinetic theory, it is assumed that average kinetic energy of a gas molecule is directly proportional to the absolute temperature. So at a constant temperature, the kinetic energy, the average kinetic energy of the system will always be constant. Okay, it is seen that on heating a gas at constant volume, the pressure increases and hence the kinetic energy will also increase. On heating the gas, kinetic energy of the particle increases and this strikes the wall of the container more frequently, thus exerts more pressure. Very simple answer. So all of these questions are very, very important because they have reasonable answers to it. Now, kinetic theory of gases allow us to derive theoretically all the gas laws. Okay, from these kinetic theory of gases, we can actually apply the gas laws to actual gases and realize its importance. Now, calculations and predictions based on kinetic theory of gases are done very well with the experimental observations and thus establish the correctness of this model. So, in this lecture, we will end this lecture here. So, from the next lecture, we will start with this topic 5.8, which is the behavior of real gases, deviation from ideal gases. So, in this topic, we will see till now whatever we were studying, whichever law we were studying, all those laws were for ideal gas. But in reality, what we actually see is that no gas is ideal gas. Okay, every gas is real gases, and only in the question paper we get the ideal gases. So in this topic, we will actually understand the real gases more closely. Thank you.